The first talk is by Oleg Drokin. Oleg has been working in the Lustre project since 2003 and is the gatekeeper of the Lustre community release. For those who are not familiar with Lustre development, gatekeeping is filtering changes to be included in Lustre. So please welcome Oleg.
Regular scheduled programming. Yeah. So I'm Oleg Drokin, and I started working on Lustre in 2003. Obviously, I didn't start as a gatekeeper. I was just a regular developer back then, doing some, code changes and stuff. Obviously, I wasn't too bad about that because I kind of rose through the ranks a bit. And in 2008, I was sent on-site at Oak Ridge National Lab as part of Lustre Center of Excellence, where we were we're deploying a new file system at the then brand new Jaguar file system that wasn't yet even installed. And many of you probably don't know or don't remember, and it's probably for the best that many don't remember anymore. But Lustre wasn't always like what it is today. It used to be that every time there's a new machine deployment or a new release, it would have been like a couple of weeks of all hand on deck, trying to contain fires, making sure things work. New at-scale machines usually failed spectacularly when trying to do file system access because nobody had been doing this kind of at-scale deployment before, and so it was always like, who knows what else will break when we'll kind of fix the current fires. So very, on-site support was really, really important back then. And so in 2011, Oak Ridge reported kind of a strange MDS race condition causing a crash that was happening about every other week. And it only happened when there was lots of file system activity, there was lots of clients connected. And as is typical, we would tell them that we would like you guys to increase your debug levels and collect us some debug information. And they weren't really super keen on that because, well, when you jack up those debug levels, everything becomes very slow. And besides, every crash means they have downtime, and the downtime at the top #1 supercomputer costs lots of money and lots of user aggravation. And I'm sure you all understand all of that. So they weren't super keen on that, and they told us that we really must do something to reproduce this outside of their system. And we thought about that, and basically two approaches have emerged internally on how to tackle this. One of them was to simulate all those clients like on a single machine. Basically, since every client is represented as a single thread on the server anyway, why don't just start a whole bunch of threads and make them do their own thingies, and hopefully that'll crash. This approach is currently known as a load client simulator, and you could access it through the Echo client and MDS survey set of scripts. The other approach that I've been spearheading back then is basically start a whole bunch of VMs, not like thousands and thousands, but still a whole bunch, and just put enough load on them and see if that will crash. So it actually did crash to my surprise, and I started to look why and discovered that really there are certain very useful things going on. And one of them is the CPU overcommit, as I call it. Basically, since I happened to run all of those VMs on a single node, and I also had Intel, back then, Intel hyper-threading thingy enabled, something that they tell you to disable nowadays because, of course, it's very insecure and stuff, but actually very useful for development. So all those VMs are competing for CPU cycles. Like inside the VM, every CPU that you give to the system is like, a regular CPU. It just runs and does instructions and stuff. But outside, it's actually an executional thread, and as it runs, the host OS tends to stop it at random times so that the other system CPUs for other VMs actually have a chance to run. And basically, what this leads to is it really, really promotes race conditions. If you have a tiny, tiny race condition in the code that is usually hard to hit, because your CPU suddenly becomes like really, really jittery, you might stop just in the right place, and then the other thread has like the other CPU that might not be preempted at the same time, and actually most often it wouldn't be preempted at the same time. It would actually do the race a lot more easily. Basically, the problems that they had every other week, I was able to reproduce in 15 to 20 minutes. Like, it was crashing like a clockwork, which obviously was very helpful into trying to find what was that about and fixing it. Obviously, you also want the code that you're actually trying to make race to be executing all the time. So if you just have some dummy load somewhere on the CPU, that's not really helpful because, yeah, you'll have like, you know, an empty cycle running. And if there are race conditions in the empty cycle, that doesn't bring you much useful information. When you're doing a setup like this, another important thing is you definitely want to have lots of memory, because if you don't have enough of memory and all the VMs don't fit, then some of them go into swap, and that makes the whole system a lot unhappy. Like, the kernel tends to touch random pages, and when the page is somewhere on swap, not in this VM, but somewhere outside on the host system, it goes to the swap, tries to read the page, and inside it just looks like a CPU stall, and you get like all sorts of warnings. It also should be mentioned that this is not the only way of doing this. The other way is like if you create a special CPU simulator that would allow you to inject pauses into your CPU stream, that would achieve a very similar result too, but nobody have seemed to be doing that. So Intel has a CPU emulator called CMix, and they talked with their developers trying to convince them that, hey, you guys really should introduce like random CPU jitterness because it's useful for development, but even they kind of didn't listen too much to me. So the only viable way right now to induce this is using a whole bunch of VMs on a single host. The other useful thing that I've been using back then and still use and recommend everybody to use is the debug kernels. And it's not just for developers, it's also very useful when you do your testing that is not performance testing, but correctness testing that nothing blows apart. The Linux kernel provides a whole bunch of extra debug mechanisms that allow you to do all sorts of extra verification. Many of them are pretty expensive, so you don't really want have that in your production setup. Some of them are not so expensive, so you still might want to have those. And also some of them you must build with, and some of them you just can turn on at runtime. Of the most important ones, the very important one is the debug page Oleg, so-called. It is really small. It is really slow, but basically what it does is every time kernel frees memory, the pages of that memory are unmapped. And then any subsequent access to that memory, which is bound to be by mistake, like use after free, instead of just passing and potentially corrupting data if it was a write, it will just crash and you will know exactly who accessed that memory, and that is really useful. The other useful setting is detecting sleeping in atomic context. So basically, if the code takes a special kind of a lock and then tries to sleep, that potentially might reroute the thread of execution onto a different CPU, or otherwise, even on the same CPU, another thread might come and try to take the same lock, and it would result in potential deadlocks all around. So this check is actually pretty lightweight, but still not enabled by default in many kernels, like distro kernels anyway. I'm not really sure why. Maybe they're just afraid of scaring people away. I don't know, but it really shows you broken pieces of code that need to be fixed, because the alternative is the bug is still there. It just doesn't show up for a long time, and then when it shows, you are left wondering, like, now, why did this task end? And you have no useful debug information. And third kind of useful, I mean, they're all useful, but the third kind of useful check that is recommended for developer setups is log correctness checks. So in kernel, there's a somewhat expensive log proofing code where it remembers in which order you take your logs, and if you happen to take them in reverse order, it'll warn you that, hey, it looks you have a log reversal pattern, so potentially there will be deadlock at times. Just check that out, and some other related checks, so also very cool. But the problem is, like, it does appear very few people enable that. And that extends not just to like Lustre developers, it extends even to distribution developers. So I've been running with this code on Red Hat 7.1, and then I switched to Red Hat 7.2, and it immediately exploded even before I was able to load Lustre. So I dig around in that, and I found that they have a broken spin lock implementation, but only if you run in a VM, so you have like, if you use a paravirtualized spin locks, they actually don't work. So I filed a bug report, and what they told me is, oh, you are running in unsupported kernel config. We don't support this config, so your bug report is invalid. That makes no sense, right? Because it's not like if I compile a non-debug kernel or use their default non-debug kernel, the bug would go away. It's just a lot easier, it's just a lot harder to hit that, but it's still there. It took a bit of time to convince them that the bug was real, and eventually they fixed it in 7.6, I believe. So for just 3 releases, paravirtualized spin locks just weren't working well, and lots of people didn't notice, I guess. Or maybe they did see random crashes, and they were like, oh yeah, well, things crash, who cares, right? That's probably how it works in the cloud. It dies, and they just spin a new instance, and that's it, right? Which is the obviously big place for running those VMs. Anyway, so returning back to the original problem back then at hand, the new setup really created lots of crashes with just 10 VMs running in parallel. Oak Ridge crash was part of them, and we were able to quickly contain it and fix it, and Oak Ridge was happy. But all those other crashes that were happening were still there, and so we, unlike often happens, or maybe not so often, I hope not so often happens, we didn't ignore them, we didn't file them away, like look at that stuff later. We actually took them seriously, and we started to fix them, and the frequency of crashes started to go down, but the whole opportunity created by this approach was too good to pass up. And so I started to run this regularly on all of our code commits back then. And probably at about the same time, somehow I started slipping into the whole role of the gatekeeper as opposed to, just a regular code contributor. And the whole approach got the name of the boiling pot, because that's really what it is. It runs a whole bunch of random Lustre code, simming together in this pot of VMs, trying to see what will break. And so over time, as we were fixing those issues, the time to crash started to really, really rise. And eventually, the metric became not how many minutes it takes until the next crash, but how many crashes in total across all VMs we would have in a day. And we also increased number of VMs. So nowadays, we run 140 VMs in parallel, and we have about 5 crashes a day at most, I say. But there are days where there are no crashes, and there are days when there are some more crashes. As you could imagine, that had a big contributing factor into Lustre stability. And the whole change happened somewhere at around 2.1. Earliest releases, like 2.11, is when I found one of the very first attempts to do this. And I started, kind of rather quickly, I switched from testing the current release into like, these are the new patches that we are going to accept soon. So let's just put them on a branch and see how they perform. And that's basically what's the birth of actual Lustre integration testing that we weren't doing before, that I'll touch on in a moment. So, an overview of how we were doing things before this whole thing. Obviously, Lustre wasn't super stable back then at new deployments, and there was a realization that, well, this cannot continue. So at around 2007, maybe 2006, all developers at Cluster File Systems, which was the original Lustre company, got training in so-called team software process. This is a Carnegie Mellon University program that teaches you how to do like real-world programming without bugs, instead of toy projects that they actually let you do at the universities. It taught you how important it is to do proper multi-stage design, how to do code reviews and inspections, how you utilize checklists so that you have stable results. They had all sorts of interesting metrics like bug densities and how you extrapolate like number of bugs you found to see how many potentially hidden bugs are there in the code that you have not found. Kind of a very interesting theory, and we tried to implement it with somewhat mixed results. And the eventual process that we've settled on was basically the patch would be submitted by a developer and it would get into automated testing, which is already a big violation of the whole TSP principle, which was that you do your code reviews and inspections before you even compile the code, because it allows you to see all the defects, as they called the bugs back then, and would improve your metrics tracking. But in real world, people don't do that. People still would pass things through the compiler just to double check them. And so we decided, okay, we'll let people to compile code, everything, and even start running some testing. And of course, developers mostly settled on, we'll wait until the tests actually run before we do any reviews at all, because what's the point of reviewing the code that might be broken that automated system would detect? And this testing actually does take quite a long time. So the whole thing was delayed. After all the reviews have been passed and stuff, patches were selected for landing. They would, like Gatekeeper would get somehow tagged and notice the patches that are that need to be landed, and would select them somehow and land them in some random order. And there was really no integration testing beforehand back then. Basically, everything would land on the branch, and then a full test suite would be triggered. And if something happened to be broken because the patches didn't interact well with each other, everybody is affected. So that really wasn't ideal. And this is why switching to boilerplate pre-landing integration testing was such a win too. Is basically all those breakages were found, well, maybe not all of them, but many enough of those breakages were found way before they would affect every developer. You could access those boilerplate branches nowadays if you are interested in, and they're called master next and B212 next. They're throwaway branches, so don't base anything on top of them, but you could see what would most likely be included into next round of landings after the testing completes. And yeah, it really did help quite a bunch versus the main branch breakages. The other thing that we do differently at WAMCloud is the static analysis. And so, returning back to how it all appeared, if you remember, the Caverity came out with this novel idea in 2003-ish, maybe 2001 even, that Basically, they have this stupid computer program that had rules that would highlight areas that don't fall within the rules. And the premise was that, yes, the computer program is stupid and it couldn't understand anything, so it has a whole bunch of false positives, but those false positives make people look into the code, and while the false positive is still false positive, they tend to notice that, well, something is still not right and find other bugs. There was a big uptake of this, and like many other tools have sprung up. But then somehow over time, the tool changed from this like stupid computer doing stupid checks into a tool for managers to measure code quality. I'm not quite sure how the transition happened because I'm not a manager. And maybe it has something to do, with pretty metrics that everybody likes to see on the tables and do like pie charts and stuff. But anyway, that happened, and the offerings have changed correspondingly. So tools started to give you more and more tables with like graphs and stuff, and that's a lot less useful for a developer. Yeah. So the not so useful thing about this is people started to run this on a code base after everything had been landed, like every other week or so. And the problem with that is once you have a bug in the code base, it's a lot harder to get it out than if you catch it before it gets there. Because the developer have moved on, everybody like treats it as somebody else's problem, they get deprioritized and all this sort of stuff. So it's our belief that the proper way to run this is to have this checked on every patch. And this is what we do at VMcloud. We use an unconventional tool called smatch, which is a special open source tool. It specifically targets Linux kernel, but you could use any C project through that, and I believe Wine uses this as well. It's on the bleeding edge of research in the area, so whenever new techniques come, they use them. For example, they were the first tool to detect when you actually have holes in the structures that you don't zero, that then cross some imaginary user space or network boundary and leak sensitive data on the stack. And we decided that it was okay to have some false positives because computers are stupid after all, but we shouldn't have too many, so we kind of filter out the known ones, but every new one needs to be explained before we accept it into the blacklist. And we also make the whole thing report into the Gerrit, which is where we review our patches as line comments. The comment appears within 5 minutes of when you submit a patch, and it does help with the turnaround. So here's a simple example where somebody had a typo, and on the error exit pass, where they were supposed to unlock a lock, they actually did another lock. So if this code pass were to be executed, this would be a deadlock. But because it's an error exit pass, it usually is not executed, and this is why those error exit passes are the places that hold the most bugs, because nobody tests them most of the time. And so it would probably have been leaving if it wasn't caught in the actual review. So this is the other interesting example. Somebody changed the structure definition somewhere else, but the warning was generated here to tell you that, hey, this place right here now seems to be assuming that a certain structure should be one size, but it's actually smaller, so this would be a buffer overflow. And it's like totally not obvious here because no changes here. And where the changes are, you don't even know that it's it's being accessed like this. So kind of very cool. And also you see a quick turnaround. So about 2 hours later, a reviewer rechecks the finding, marks it as hey, this is indeed a problem. And then another developer, the original developer, who is in a different time zone, wakes up in the morning and submits a new version patch that's fixed. So it does promote bugs actually being proactively fixed way, way before they actually make their way into the code base and got in testing. This is the other important thing I wanted to touch on. We often split tests into two sets. One is a smaller review testing, and one is a full testing that runs on every commit. And while we strongly enforce review testings to be fully green, so like there are no failures for an accepted patch, the full testing happens afterwards, and as it happens to be, nobody actually looks into the result, or almost nobody looks into the results, because developers certainly don't care. QA people are always overwhelmed with other things, and the end result is basically out of sight, out of mind. People just, don't notice something's broken, and like full test suites are noticed to be broken all the time, and I even believe like they're probably already broken in all sorts of different ways, just nobody have noticed that. The other problem is like when you have a monoculture of testing, tests tend to be fine-tuned to just pass in this particular configuration. So when you add a different configuration or somebody actually runs it in the real world, all of a sudden things break, and like we look into it like, hey, but we test this, but apparently it's just a tiny change in the configuration and suddenly things break. And this also was a big win for the boil pod, because it was a totally different configuration and suddenly all sorts of other things crept out. It's also very important to give developers easy information to all the problems that they see. Right, like Lustre is a really, really complicated system. It produces lots of logs, and nobody could be expected to review logs for every test run. So we need to have easy tools to quickly search through those, and to quickly cross-reference things. Things like, hey, how many command not found do our tests produce and still not fail? So actually, I spoke with our QE people and asked them like, hey, we need to test full text search. And they told me, do you even know how many logs we generate? It's tens of gigabytes per day. There's not possible to actually search through that. Which isn't actually true, because I was able to find products that allow us to do that, but it shows you a different mindset, because I'm not sure, probably they don't use this as important, because they are not the ones that are digging through those reports. Also, automatization goes a long way. You really want to automatically extract all sorts of information from crash course and things like that, because otherwise you get a report, something's broken, or maybe something got a compile error. So you get a link, you press a link, it brings you to another page, you select which distro broke, then you go into that, you go into individual build, and it's like 5-6 clicks until you even see what the compile failure was. It's like just a total waste of time. So I was very frustrated by the whole thing, and I decided that, well, if you want to do something, if you want something being done well, you just do it yourself. I guess the other thing is like you pay somebody, but well, I had no money. No free money anyway. And so I set myself some simple goals, like, because people are lazy, I just want to give them results real fast, like compiling under 5 minutes, general fatal problems like within 10 minutes, and overall finished in like 2 hours of testing. This is so that they didn't totally switch to something else. And also gives them all the data they want in very super convenient places to access, and minimize useless chatter. I also thought that it'll be like a human-guided compliance. That part didn't work as well, but anyway. So I also wanted to use minimal resources, and well, I'm scrolling through this fast because they actually keep showing me warnings that I'm kind of running out of time. Anyway, so lots of memory, and the numbers do look extreme, like terabytes of memory and stuff. But it's surprising that you could actually buy like 80 CPU cores and a couple of terabytes of memory and things like that just for a price of a single modern MacBook Pro. Like really, for $3,000, you could buy 8 Intel CPUs with 10 cores and hyper-threading and 2 terabytes of memory, and kind of that gives you tons and tons of CPU power. well, they are kind of power hungry. So on the left is my old failed attempt. Like I thought, I'll save money by not having the cases and stuff, but well, most expenses are in the CPUs and motherboards anyway, so those customer-oriented motherboards actually don't take much memory, so that was a failure. But on the right-hand side, you can see at the very top are two of the open computer racks, and in the middle there's like a Supermicro 4-node in a 2U form factor. Those two altogether give me about 280 test clusters, each consisting of 2 VMs. So there's like 2 terabytes of memory right there. And the other boxes are just supporting Singis. And if you need pictures, I could actually give you full resolution ones. The utilization was kind of surprised. I didn't expect more than like 4 or 5 sessions being run all together, but here we could see that it quickly, often rises to like 20, but still the delay for runs isn't too big. So in here you see there's like a shadow spike at the bottom for the tester stats. So the runs were delayed at most for half an hour, and the compiles were delayed even less. So it seems to be mostly working towards my target goals. And here's the sample interaction that actually shows people using this almost as intended and more. So here we see Neil Brown using my compile box as his compile box because it actually builds things faster than you could do on your local system because I actually optimized for like quick build times. And so there, we can see first iteration, it fails building, he gets report very fast. Second iteration, it crashes early on and he gets report very fast, and next minute he uploads another version. And then it again crashes, but in one of the codes that he actually introduced. And so the crash dump, the backtrace information even posted right away into one of the comments for him to see. And then he kind of moves on until it actually stops crashing the second you actually try to load Lustre. So it was kind of interesting to see more people shifting their development pattern into this because, I mean, we've seen this before, but our old system wasn't as quick as the turnaround time. And this is the information that you see when the session doesn't fail right away. So like what failed, what passed, like immediately. No extra clicking, but if you do decide to click again, a very dense page with lots of information as opposed to like click into every test and start to see what was actually going on there that we have on our regular testing system. Anyway, so what I learned is people do take a path of least resistance, and they, even if they appear to be caring, they don't care all the time. So. And this is where I believe the CMU TSP course was kind of misguided by kind of trying to offload as much work as possible into people. That just goes contrary to human nature. So you need to always assume the worst. You need to assume that nobody have even compiled tested this code, let alone actually tried to run it in some sort of simplistic test environment. So you really need to have lots and lots of automation to guard you from those, because everybody has periods where they kind of can't look into things as much as they should have. This includes everybody, the developers, the gatekeepers, the testers, everybody has periods like that. So the more automation you have to guard you against that, the more chances are that bad things would be caught before they get to do any real damage. And the other thing is you shouldn't decouple QA and developers too much. And that's not to mean that they shouldn't be separate people, but don't place them totally far apart and do let them kind of have strong influence on each other. It definitely leads to much better results than if they're like really separate people and certain trends emerge that, oh, those pesky QA guys, they keep filing those tickets that detract me from the real work I'm supposed to be doing and I have my deadlines. Or, oh, that gatekeeper keeps skipping my patch because he comes up with those strange ideas about what it should be doing correctly. But who cares about that? My deadline is really looming and the release is out next week and I'm going to miss it if I kind of don't get this patch accepted. So this is not really productive, and you really need to kind of make them work together in some ways. I mean, in more ways than are often made anyway. Yeah, so that's kind of very important in my view. And this is why I kind of even did a whole bunch of things that I showed you, because, you know, I found it's really, like, when you do separate things too much, it's so hard to make the other party do what you want. And they don't even view it as important. Like, I tell them it's important, but they still have their own goals, their own deadlines, and you know, it just gets delayed and delayed. Anyway, that's it.
Okay. Only time for one question.
Okay. Oleg, what if your advanced testing produces so much warnings and schedules during atomic operations, and so much noise that it is impossible to actually analyze it?
It doesn't really produce too much noise, but for the broken code, it does produce the warnings. They are, like, if you've noticed here, you see it says, well, like, server memory leaks detected in yellow. This means that this is a long-standing issue that has been there for some time. If a new thing like that appears somewhere, the color would change into red. So I have, like, special tracking to see, have we seen these warnings before or not? And similarly with the failures, doesn't show any on the right, but like, if a certain test fails, it will be displayed in red if it's a new failure not seen before, and in yellow if it was seen before.
Yes, it was very useful for my patch, actually.
Yeah,
yes, but you have a baseline of that noise. And
right.
Is it high?
The noise? It's not as high, so basically there are maybe 3 or 4 tests that produces constant warnings. So conf72 memory leak is one of them. There's the shared key sleeping in atomic context is another one. It only happens in shared key, and hopefully somebody eventually will fix that, but this is not a very common last year usage scenario, so I guess it hasn't been on anybody's radar. And then there are a couple of failures that happen from time to time, and yeah, well, not the rsync, but replay dual that didn't make the list here often times out. But the floor is not too high, and you get hopefully a lot of very clear distinctions when the problems are most likely related to what you are seeing. I mean, to what your patch actually changes. But if you do have some feedback on how to better fine-tune that, definitely write to me and I'll look into it. This is intended to be helping developers, and I'm still one of the developers. So while I believe I have good ideas, I'm sure other developers might have feedback, so definitely send your feedback my way.
Thank you.
Thank you, Oleg.